So, here if I look at this, I superimpose a set of parallel lines and get the measure PL, number of intersections of the lines with the grain boundaries per unit length using this line grid. One measure of grain size can be, and that is actually an important measure, which could be that when I put this grid of parallel lines, I measure these lengths intersected within the grain. Okay. So, I measure these intercepts L1, L2, this is L3, this is Li, and so on. And I can define a grain size measure as what is called as the mean intercept length. L bar, which is just nothing but summation Li. If I have n number of intercepts, take an average value. This is the mean intercept length. This is very commonly used, particularly if you are doing structure property correlation. This is a very important measure for grain size as the mean intercept length. Now, this thing is, how do I measure this mean intercept length? Do I individually measure these lengths, or can I have a counting, a simple counting procedure? We try in stereology to always go wherever possible, go for a counting procedure, whereas I simply have to do counting, because then that is less error prone, it is very fast to get the grain size. Now, this should be very clear that if I measure PL, then mean intercept length would be nothing but simply 1 upon PL. So, I do not have to go and measure these individual lengths. I will simply count the number of intersections I get with the grain boundaries, divide by the total length of the grid line, I will get PL, reciprocal of that would simply give me the mean intercept length. Okay, so, you see the grain size measure here, mean intercept length is 1 upon PL, which is also now related, as you can see, this measure is related to surface density of grain boundaries, because surface area per unit volume SV is equal to 2 times PL. Hence, you will get mean intercept length to be equal to 2 upon SV. So, mean intercept length is inversely proportional to surface area per unit volume. Okay. Now, I would like to use the same mean intercept length for these particles. Okay. If I have now particles and I want to get some kind of an average size for these particles, and these particles are of irregular shape. So, how do I? So, I can again put, let us say, we will explain this in this manner. I can put a grid of lines, or I can simply put one line. I measure these lengths. Okay. Again L1, L2, Li and so on, then I can get a measure of the size of these particles as mean intercept length as summation Li upon n. Now, here the mean intercept length will not be equal to 1 upon PL. This will work only when you have space filling grains. Here you have this other phase, these particles are embedded in some phase. Now, but I would like to still evolve some kind of a counting procedure for this. Now, this is done in the following way. Let this total length of this line be capital L. Okay. And what I do here, I divide the numerator and the denominator by this length of my line. Okay. This is what I do. Now, let us look at these two quantities separately. What are these quantities? What is this quantity in the numerator? The lengths intercepted within the particle, sum total of those divided by the total length of the line that I have superimposed. That is what? That is called the length fraction. So, let us write this, that is the linear fraction. What is n upon L? We are going to assume here that these are all convex particles. How many, if there are, I intersect n particles, how many intersections I have with the interface boundary? 2 times n, right. This is one intersection with the particle, but it produces 2 intersections with the phase boundary, is not it? So, if I were to measure PL, what is PL equal to? PL would be equal to 2n upon L, right. So, n upon L, this term would become what? PL upon 2. So, this would become PL upon 2, number of intersections with the phase boundaries. What can I replace this linear fraction with? I can replace the linear fraction with volume fraction, which I can replace with point fraction. So, my numerator will become point fraction, this 2 will go up, and at the bottom PL. So, now my measure of particle size in terms of mean intercept length is given by an expression 2 times the point fraction upon number of intersections per unit length of the test line. This again is a, I have replaced this method with a counting procedure. So, if I look at this slide here, so it is 2 p sub p upon p sub L, which since point fraction is volume fraction, I can also write it in terms of volume fraction, and PL, remember that instead of PL I can write surface area per unit volume divided by 2. So, this becomes 4 times volume fraction upon surface area per unit volume. Okay. So, here to get this average particle size, I just have to measure point fraction, I just have to measure PL, I do not have to do anything else. So, very simple method of getting some kind of an estimate of particle size. So, if I am doing some work in which I am maybe trying to see how my particle size is evolving as a function of some processing treatment I am giving, then this will be quick measure for measuring the particle size, only counting is required. So, what you do, you put a grid here, the same grid you use to get PP and the same grid you use to get P sub L, that is it. And let us look at now something where the relationship was given to you, and let us see how we got this particular relationship. The average diameter of the graphite nodules is given by 8 upon pi times the point fraction over PL. Okay. Here if you look at this slide, this is the expression that we just now got for the mean intercept length of particles. Now, I am trying to get this. In order to get this, I have to somehow relate the particle size to the mean intercept length. Now, if I have circular particles, I am assuming circular particles here, then what is the relationship between the diameter of the particles and the mean intercept length. So, just the way we did for a sphere, remember we got average particle area, here I am talking about an average intercept length. So, again the intercept length, what it would be would depend on when the line is passing through the particle, how far away it is from the center of the circular particle. Okay. So, let this be x, this is d by 2, d being the diameter, and this length is L, the intercept length. So, clearly I can write the intercept length in terms of d and x so right 2 times d by 2 square minus x square to power half, and twice of that because this will give me just a half the length. So, make it twice. Then we go through this exercise of finding out the mean intercept length L bar. I need to integrate over all possible values of x going from 0 to d by 2. This factor of 2 can come out, and out here it is d upon 2. I just have to integrate this again. This is a simple, really a simple integral. You just have to substitute, again do this substitution, it becomes straightforward. X is equal to d by 2 cos theta, just plug it in this, and you will get mean intercept length to be equal to pi by 4 d. Okay. So, the mean intercept length is equal to pi by 4 times the diameter, and we already know that mean intercept length can be written in terms of 2 times the point fraction upon PL. Okay. So, diameter is actually 4 by pi L bar. Substitute for the mean intercept length in this, and this will become 8 upon pi times point fraction upon PL. So, this is another of the derived relation where you can get diameter average and in fact, since particles are of varying diameter, this will give me average diameter of all those graphite nodules if we assume them to be circular. Okay. So, that is one more of the derived parameters. While we are at this particle size and we also discussed grain size, I should give you 2 more grain measures which have been used, some other grain measures. One is what is called as the other than the mean intercept length, one is what is called as the Jeffreys grain size. In Jeffreys grain size, you measure NA, number of grains per unit area. This would give me an average grain area to be simply the reciprocal. This is I am talking about a single phase polycrystalline structure where there are space filling grains. Then the average grain area would simply be the reciprocal of this. And Jeffreys grain size simply tells me that you take the square root of this average area as a grain size measure. Okay. There is another important measure, this one is probably more important than Jeffrey's, is what is called as the ASTM grain size number. This is a very old measure. It is not very useful if you are doing some structure property correlation stuff, but why I am mentioning this is that this is still used in industry. Many industries still use it as a quality control measure, and this is defined in the following way. ASTM grain size number, I will designate that as G, then this is given by the following expression: N is equal to, I should write N 100 is equal to 2 to power G minus 1. G is the ASTM grain size number. N 100 is the number of grains per inch square at a magnification of 100x. Okay. This is a very old measure, and since it is still used in industry, so you should know this. This measure tells me that when I get larger number of grains per unit area per inch square, then my G will be larger, and if N is small, then G will be small. Now, if N is large, which means grains are smaller or bigger? Grains are smaller. So, larger is this grain size number, smaller is the grain size. Okay. You will learn more about this in the demonstration exercise that will be followed. One final derived parameter that I will just mention, the mean free path. So, if you have particles which are dispersed, precipitates let us say which are dispersed in a matrix, what is the kind of a mean free path which kind of represents maybe dislocation movement from one particle to another particle where it is hindered. So, mean free path becomes important from that point of view. It represents an uninterrupted interparticle distance through the matrix averaged over all possible pairs of particles. Okay. And the relationship for this mean free path is again can be obtained by simply a counting exercise. So, the mean free path lambda is given by 2 times 1 minus the point fraction divided by PL, the number of intersections per unit length. Okay, so, this is an important can be an important parameter if you are, let us say, doing some mechanical behavior studies. Now, before I complete this lecture, I just want to introduce something that in many of our measures we have to do this NA, counting of number of grains, counting of number of particles. So, we must know the proper method of counting, an unbiased way of counting particles, because the problem comes when in any region that we are trying to count where only half the grain is inside or part of the grain is inside. So, methodology for counting of grains and particles. So, I have let us say a polycrystalline microstructure. I need to put some kind of a frame, a counting frame on this to get number of grains per unit area, let us say. And this is the kind of counting frame that you put. Okay, this is a little peculiar looking frame. This is the red line and there is a green line specified here. These are the dimensions of the frame. So, you know what is the area of the frame from these dimensions. Now, I have to count, so which grains I count, which grains I do not count, what happens to the grains at the edges. So, here the red line represents what is called the exclusion zone, that any grain which touches the red line will not be counted. All grains which are completely inside count as whole, all grains which touch only the green line will be counted as whole. So, Going with this, I will not count this grain. All of these grains which are marked red will not be counted. These grains will be completely counted as whole. Grains completely inside will be counted. Going with this, you would get, for this particular area, number of complete grains inside the frame which are light green are 60, number of grains in the inclusion region dark green is 20, number of grains touching an exclusion region red ones, N3 is 14. So, 14 I will not count, but I will add 60 and 20 together to get a total of effective number of grains as 60. This, if I divide now by the area of the frame, which is 246 into 219 micrometer square, then I will get this result of 0.0015 per micrometer square. If I take the reciprocal of this, remember this is actually essentially Na is what I have done. 1 upon Na is the average grain area. So, 1 upon 0.0015 gives me about 667 micrometer square as the average area of the grain. So, from here you can go to ASTM grain size and any other parameter that you wish to. A similar methodology you would use for counting of particles. If I have now these particles, dark particles, put again the a counting frame of the similar nature, again these red ones which are marked are gray particles which are touching the exclusion zone and they will not be counted. The dark green ones will be counted because they are only touching the inclusion zone, and of course all particles which are completely inside the frame will be counted, and hence you get 88 light green particles, 7 dark green, these are to be counted, the red ones not to be counted, there are 14, and you get effective number of particles inside the frame as 95. You want particles per unit area, then it is 95 divided by the area of the frame, 505 into 450, giving me 0.00042 per micrometer square. So, this counting methodology gives you there are other methodologies you might find for counting, but this methodology turns out to be the best methodology, but gives you the unbiased, there is no bias involved in this counting, it is a very objective methodology to count and it is an easy methodology to count. So, with this I complete this lecture, and in the next lecture you will be seeing you will be doing an exercise on the various things that we have done in this lecture. Thank you.